There's a place where the Earth ends and something else begins. Not a sharp edge, not a sudden door, just a gradual thinning, a dissolving of what we know as air into something quieter. This boundary has a name, the Kármán line, about 100 kilometers above the surface, 100 kilometers up, and the world changes. Space begins there officially, formally, though of course there's nothing official about the universe itself. 100 kilometers. You don't need to remember that number. It can drift away if it wants to. The line is there, whether we hold it in mind or not. About 100 kilometers high, that's where space is said to begin. The Kármán line, they call it, a threshold we've named. The atmosphere fades, the familiar blue gives way to black. 100 kilometers above the Earth, nothing here requires your attention. The line doesn't move. It's been there long before we noticed it. It will remain. Let this settle. There's no hurry. Now, if you were to rise past that line into weightlessness, something curious happens to the body. The spine, the column of bone and cartilage that holds us upright on Earth, begins to stretch just slightly, just a few centimeters. In the absence of gravity's constant pull, astronauts grow taller, not dramatically, a few centimeters, 2, perhaps 3. Their spines decompress, expand gently. Astronauts become slightly taller in space. The spine stretches, up to a few centimeters. Weightlessness allows this. The body responds to the absence of weight. You can let this image rest. There's no test later. No need to picture it perfectly. The spine decompresses in weightlessness. A few centimeters of height gained. Temporary, gentle. The body adapting to a place without up or down. Let that be enough. Far from Earth, telescopes drift in silence. One of them, Hubble, has been watching the universe for years, decades. And what it saw changed something fundamental about our understanding. The universe is expanding. We've known this for a long time. But Hubble's observations revealed something more, something stranger. The expansion is accelerating, getting faster, not slowing down as you might expect. Faster and faster, the universe spreads outward. Hubble showed us this. The universe doesn't just expand. Its expansion accelerates, speeds up over time. There's probably a reason, something called dark energy. Though what that is, well, that's still mostly mystery. But the observations are clear. The expansion accelerates. The universe grows faster and faster. Hubble observations revealed this: an accelerating expansion, likely driven by dark energy. You don't need to understand why. Even scientists are still working on that part. It's enough to know the universe is opening outward, faster and faster, into something we can't yet see. Let it expand without you. Rest here. Another telescope now, newer. The James Webb Space Telescope. It looks even farther back than Hubble could, farther into the past. In its images, galaxies appear, young galaxies, galaxies that formed only a few 100 million years after the beginning, after the Big Bang. A few 100 million years sounds like a long time, and it is by human measure. But in cosmic terms, it's very early, remarkably early. The James Webb Telescope shows us galaxies from just a few 100 million years after the Big Bang. Young galaxies, early formations. These are among the first structures to light up in the darkness, the first gatherings of stars. You don't need to hold onto the timeline, the numbers can fade. What remains is the image, very young galaxies, seen across an almost unimaginable distance. galaxies just a few 100 million years old, cosmically speaking. Webb shows them to us. Ancient light finally arrived. There's no rush to process this. The light has already traveled for billions of years. It can wait while you rest. And speaking of that light, the James Webb Telescope sees light that has been traveling for over 13 billion years. 13 billion years in motion, crossing the void. Light that old. Over 13 billion years of journeying through space. And now, finally, it reaches the telescope's mirrors. The Webb telescope can see this light. Light over 13 billion years old. Light from when the universe was very, very young. 13 billion years. It's a span beyond easy comprehension. You don't need to grasp it fully. Just let it sit there. Vast, distant. Over 13 billion years of travel. The light keeps moving, and eventually, after all that time, it arrives. Webb captures it. The universe is patient. The light is patient. You can be patient too. Now, the space between things, the cosmos itself, what fills it? Mostly hydrogen and helium. The lightest elements, the simplest atoms. About 3/4 of the visible matter in the universe is hydrogen. Hydrogen everywhere, filling the cosmos. 3/4 of what we can see in terms of matter is hydrogen. The universe is full of it. Helium too, but mostly hydrogen. Roughly 3/4. The vast majority. You don't need to remember the fraction exactly. The point is simple. Hydrogen dominates. It's the most common element in the visible universe. 3/4 hydrogen. The rest, helium and trace amounts of everything else. But hydrogen is the foundation, the cosmic abundance. Hydrogen filling space. 3/4 of visible matter. Simple, light, everywhere. Let this be simple. Hydrogen, helium, the stuff of stars. But space is not entirely full, even with all that hydrogen. Between the stars, the interstellar regions, they seem empty, almost empty. In every cubic centimeter of interstellar space, there are only a few atoms, on average. Just a few. Per cubic centimeter. Interstellar space is not completely empty, but close. A few atoms per cubic centimeter. That's how sparse it is. A cubic centimeter is small, about the size of a sugar cube. And in that volume, out there between the stars, only a few atoms exist. This is what we mean by emptiness in space. Not true emptiness, but close. A few atoms per cubic centimeter on average. Interstellar space, nearly empty, with only a few atoms in each small cube of volume. You can picture it or not. Either way, the emptiness remains. Quiet, sparse, waiting. Yet even in that near emptiness, there are places where matter gathers. Huge clouds, molecular clouds made of gas and dust, floating between the stars. These clouds are vast, enormous. And within them, something happens. New stars are born. Molecular clouds of gas and dust spread between the stars. Regions where stars form. Stellar nurseries. The clouds are mostly gas, mostly that same hydrogen, with dust mixed in. And slowly, over time, the cloud collapses in places. Gravity pulls, and stars ignite. Between the stars, there are these giant molecular clouds, gas and dust. Within them, new stars come into being. Giant clouds, star-forming regions, gas and dust gathering, collapsing, igniting. Nothing here is fast. Star formation takes time, millions of years. You can let go of the timeline. It's enough to know clouds exist, and within them, stars are born. Let the clouds drift in your mind, slow, unhurried. Within some of these clouds, astronomers have found something unexpected. Complex organic molecules. Not life, but the building blocks. The pieces that might someday become part of biochemistry. Complex organic molecules in molecular clouds. Molecules that could be precursors. Potential building blocks for later biochemistry. They're floating there, in the cold and dark. Organic molecules, complex ones. Components that, in the right conditions, might contribute to life eventually. These are not living things, just molecules. But they're more complex than simple hydrogen or helium. They're made of carbon and other elements bonded together. Astronomers found these molecules in some molecular clouds. Building blocks, they call them, for possible biochemistry later on. You don't need to know which molecules exactly, just that they're there. Complex, organic, waiting perhaps for the right circumstances. Organic molecules in the clouds, building blocks for potential life, found between the stars. Let them float, let them wait. There's no urgency in chemistry that spans millions of years. Now pull back, way back, to the whole universe, to something that fills every corner of space. There's a faint glow, an echo, a signal from the very beginning. The Big Bang left behind radiation, a weak echo that still fills the entire universe. This is the cosmic background radiation, a faint remnant of the Big Bang. It's everywhere. The background radiation is an echo, a weak one. From the universe's birth, it fills all of space. You can't see it with your eyes. It's not visible light, but instruments can detect it. This faint glow, this remnant, the cosmic background radiation, an echo of the Big Bang, filling the universe, faint, persistent. The universe remembers its own beginning, in a way, through this radiation, this echo. There's something almost comforting about that. A signal from the start, still humming quietly through space. Let it hum. You don't need to listen closely. This background radiation, this echo, has a temperature. Today, it's about 2.7 degrees above absolute zero. 2.7 degrees Kelvin. Absolute zero is the coldest possible temperature, and the cosmic background radiation is just 2.7 degrees warmer than that. Barely warmer. The cosmic background radiation has a temperature of about 2.7 degrees above absolute zero, 2.7 degrees Kelvin. Nearly as cold as anything can be, but not quite, just slightly above. This is the temperature of the universe's ancient echo, 2.7 degrees, cold, quiet, everywhere. You don't need to remember the number, just the sense, very cold, almost at the lowest limit, a faint warmth from the beginning, about 2.7 degrees above absolute zero. The temperature of the cosmic background radiation today. Cold space, cold light, drifting. Now, something denser, something that bends space itself. Black holes. Objects so massive, so compact, that nothing can escape them, not even light. Some black holes are truly enormous, billions of times the mass of the sun. Billions. They often sit at the centers of galaxies. Black holes can be billions of solar masses, supermassive, often located in galactic centers. Billions of solar masses. Hard to picture, hard to hold in the mind, but they exist. These immense black holes anchoring galaxies, a black hole with billions of solar masses, sitting at the center of a galaxy, pulling, warping space-time. You don't need to understand the mechanics. Just the scale, billions of times the sun's mass. Central, massive, black holes that massive often reside in galaxy cores. Supermassive black holes, billions of solar masses. Let the scale wash over you. Don't try to grasp it fully, just let it be immense. And the most distant supermassive black hole we know of, it shines as something called a quasar. We see it from a time less than 1 billion years after the Big Bang. The most distant known supermassive black hole, visible as a quasar, from less than 1 billion years after the universe began. Less than 1 billion years after the Big Bang, and already a supermassive black hole existed. We see it now as a quasar, shining across the universe. A quasar is a bright core. We'll come to that. But for now, the most distant supermassive black hole, shining from that early time, less than 1 billion years old, cosmically, and already supermassive, the most distant supermassive black hole we know, a quasar, from less than 1 billion years after the beginning, early, distant, massive, shining. You can let it shine without watching closely. Rest. Quasars then, what are they? Quasars are extremely bright cores of distant galaxies. At the center, matter falls into a supermassive black hole. As it falls, it heats up, becomes incredibly bright. Quasars, extremely bright galaxy cores, powered by matter falling into a central black hole. Matter spirals in, falls toward the black hole, and in that process releases tremendous energy, becomes luminous, blazingly bright. Quasars are among the brightest objects in the universe, extremely bright cores, powered by black holes consuming matter. The matter falls in, the black hole pulls, and light pours out from the superheated material. Quasars, distant, bright, driven by matter falling into supermassive black holes at the centers of far galaxies. You don't need to visualize the mechanism, just know. Quasars are bright, very bright, powered by black holes. Let the brightness fade in your mind. Let it rest. Galaxies themselves gather in groups, sometimes thousands of them, bound together by gravity. Galaxy clusters, thousands of galaxies, held together, surrounded by hot gas. A galaxy cluster can contain thousands of galaxies, bound by gravity, with hot gas filling the space between them. Thousands of galaxies in one cluster, orbiting one another, slowly, over billions of years. These clusters are held together by gravity, mutual attraction, and between the galaxies, hot gas glows faintly. Galaxy clusters, thousands of galaxies connected by gravity, surrounded by hot gas. Thousands, bound, drifting together through the universe. You don't need to count them, just let the number settle. Many galaxies, together. Our own galaxy, the Milky Way, belongs to a cluster, a smaller one, called the local group. The Milky Way is part of the local group, a galaxy cluster, which itself belongs to a larger structure called a supercluster. The local group, our galactic neighborhood, which is part of something even larger. The Milky Way sits within the local group. That group is part of a supercluster, layers of structure. Local group, supercluster, nested gatherings of galaxies. The Milky Way among them. We're part of something larger, and that larger thing is part of something larger still. You can let the structure fade. We're here. That's enough. Now, something invisible, something we can't see directly but know is there. Dark matter. It makes up most of the matter in the universe, but it doesn't emit light, doesn't shine. Dark matter. The majority of the universe is matter, no light. Detected only through gravity. We notice dark. Matter through its gravitational effects. It pulls on things, bends space, but doesn't glow. Dark matter makes up most of the matter around us, in the cosmos. Yet it's invisible, dark, known only by its pull. The majority of matter is dark matter. It doesn't radiate. We see it only through gravity, invisible matter, most of the matter that exists, felt, not seen. You don't need to picture it. How do you picture the invisible? Just know it's there, silent, heavy, everywhere. And then there's something even stranger. Dark energy. Dark energy contributes even more to the universe's total energy than dark matter does. And it's driving the universe's expansion, making it accelerate. Dark energy. Even more abundant than dark matter in terms of energy. Driving the accelerated expansion. We don't know what dark energy is, not really. But we see its effect. The universe expands faster and faster. Dark energy makes up more of the universe's total energy than anything else. And it pushes outward, accelerates expansion, more energy from dark energy than from dark matter, accelerating the universe's growth. Dark energy, mysterious, dominant, pushing everything apart. Let it push without resistance. Let the universe expand in the background. Radio telescopes, arrays of dishes pointed at the sky, listening to wavelengths we cannot hear. There's one planned called the Square Kilometer Array. It will map dark matter's distribution across enormous distances. The Square Kilometer Array, a planned radio telescope. It will chart where dark matter lies across vast reaches of space. Dark matter doesn't emit radio waves either, but its gravity shapes how other things move, how galaxies cluster. The array will map those patterns, trace the invisible through what it influences. Radio telescopes like the Square Kilometer Array, mapping dark matter's distribution over immense distances. The array will listen to the cosmos, and from those signals reconstruct where the dark matter must be, where it pulls, where it gathers, mapping the invisible across vast distances. The Square Kilometer Array's planned task. You don't need to wait for it. The universe isn't going anywhere quickly. There was a time long ago called the Epoch of Reionization, an early phase in cosmic history. During this epoch, the first stars and galaxies formed, and their light changed the universe around them. The Epoch of Reionization. An early time, when the first stars and galaxies ionized the neutral gas filling space. Before this epoch, the universe was full of neutral gas. Dark, neutral. But then stars ignited, galaxies formed, and their radiation ionized that gas, changed it. The first stars and galaxies ionized the neutral gas in the universe. This was the epoch of reionization, an early phase, stars lighting up, changing the chemistry of everything around them. You can let this period drift past. It happened once, long ago. The universe remembers, even if we don't need to. Deep images of the sky reveal something astonishing. Photographs like the Hubble Deep Field show thousands of galaxies in just a tiny patch of sky. The Hubble Deep Field, a small section of sky, photographed deeply, thousands of galaxies visible, just a tiny area, and yet thousands of galaxies, each one a system of billions of stars, deep sky images like Hubble Deep Field. Thousands of galaxies in a small piece of sky. The universe is more crowded than it appears at first glance. Point a telescope at any random patch of darkness, look deeply enough, and galaxies appear. Thousands of them. Hubble Deep Field showed this. Thousands of galaxies. In one small area, thousands, in just a tiny section. The sky is full of galaxies. Everywhere you look, if you look long enough. Let them populate the darkness quietly. No need to count. Astronomers use something called gravitational lensing. The gravity of large galaxy clusters bends light, from even more distant galaxies behind them. Gravitational lensing, using the gravity of galaxy clusters as a cosmic magnifying glass to see even farther galaxies. Massive clusters bend space. Light traveling through that bent space curves, and so distant galaxies behind the cluster become visible, magnified. Gravitational lenses. Astronomers use the gravity of large clusters to see more distant galaxies, a cosmic lens, gravity bending light, revealing what would otherwise be too faint, too far. The gravity of clusters acts as a magnifying glass, revealing galaxies farther away still. Space curves. Light follows the curve, and we see farther because of it. Let the light bend gently. No effort required. One such cluster, Hubble 2744, serves as a natural lens. The James Webb Telescope uses it to observe some of the most distant galaxies known. Hubble 2744, a galaxy cluster, acting as a lens for JWST, revealing some of the farthest galaxies. The cluster sits in front. Its gravity bends light from galaxies behind it. Webb looks through this lens and sees galaxies incredibly far away. Hubble 2744 serves as a natural lens. JWST observes through it, seeing some of the most distant galaxies, some of the farthest galaxies we know, visible because of Hubble 2744's gravity. Webb captures them, a natural lens in space. Hubble 2744. Webb looking through it, finding distant galaxies. The universe provides its own tools, lenses made of gravity, clusters that magnify. Rest in the cleverness of it. Let it work without you. The Webb telescope doesn't just take pictures, it observes in many different filters, different wavelengths of infrared light. Webb combines observations through many filters. From this, astronomers estimate the age and star formation history of distant galaxies. Different filters reveal different information. Combined together, they tell a story. How old a galaxy is, how fast it's forming stars. Webb uses multiple filters, combining them to estimate age and star formation history of far galaxies. Filters, wavelengths, data assembled into understanding. Age, star formation, history. Written in light. Webb's observations across many filters, used to piece together galactic histories, estimate ages. You don't need to understand the technique, just know. Light in different colors tells different parts of the story. Let the filters do their work. Quietly, precisely. Spiral galaxies like our Milky Way have something extending far beyond their visible stars. Halos of dark matter, spread out, reaching much farther than the stars we can see. Spiral galaxies have extended dark matter halos, reaching far beyond their visible stars. The stars we see are just the center, the bright part, but the dark matter halo extends much farther, invisible, massive. Dark matter halos around spiral galaxies, stretching far beyond the visible. The Milky Way has one, other spirals too, these halos of invisible matter spread wide. Extended halos, dark matter, far beyond the light. The galaxy is larger than it looks, much of it hidden in darkness. Let the invisible extend outward, unseen, unhurried. With radio surveys using the square kilometer array, researchers hope to see the first galaxies, the ones that formed just after the cosmic dark ages. Deep radio surveys, square kilometer array, seeking the first galaxies after the dark ages of the cosmos. The dark ages were a time before the first stars, before reionization. Radio surveys hope to see the galaxies that ended that darkness. Researchers want to use the square kilometer array in deep radio surveys to glimpse the first galaxies. right after the cosmic dark time, the first galaxies, shortly after the dark ages, visible perhaps in radio wavelengths, square kilometer array, searching for those first lights, those first structures. You don't need to see them yourself. They're being searched for, slowly, carefully. Some distant galaxies in the early universe surprise us. They form stars at remarkably high rates, starburst galaxies, galaxies with surprisingly high star formation rates, found in the early universe. Some early galaxies are forming stars much faster than expected. These are called starburst galaxies. Starburst galaxies, high star formation rates, found among distant early galaxies. They're churning out stars rapidly, much faster than normal galaxies. These starbursts, some distant early galaxies, surprisingly active, forming stars at high rates. Starburst galaxies, rapid star formation. In the young universe, starburst activity let the stars form without rush. Even rapid, by cosmic standards, is slow by hours. One such galaxy, HDF 850.1, is particularly bright in submillimeter wavelengths. It lies in a region with many galaxies, an overdense area in the early universe. HDF 850.1, a starburst galaxy, especially bright in the submillimeter. Located in a dense region of early galaxies, this galaxy shines brightly in submillimeter light, and it's in an area where galaxies cluster together, an overdensity. In the early universe, the starburst galaxy HDF 850.1, bright in submillimeter wavelengths, in a galaxy-rich region of the early cosmos. HDF 850.1, bright. In a crowded part of the early universe, many galaxies nearby. Submillimeter brightness, a galaxy in an overdense region, HDF 850.1. You don't need to remember the designation, just another bright point in the early cosmos, another cluster of stars being born. In starburst galaxies, gas transforms into new stars much faster than in normal spiral galaxies. Starburst galaxies convert gas to stars much more quickly than normal spirals do. The gas collapses, forms stars. But in starbursts, this happens at an accelerated rate, much faster than in galaxies like the Milky Way. In starburst galaxies, gas becomes stars much faster, compared to normal spiral galaxies. Faster star formation, gas converting rapidly, starburst activity, much quicker than in typical spirals. The gas-to-star conversion in starbursts let the gas collapse at its own pace. Even fast is still measured in millions of years. Galaxies come in many shapes. Not all are spirals. The forms of galaxies range from thin disks to elliptical balls to irregular, chaotic structures. Some galaxies are flat disks. Others are round, elliptical. Still others have no regular shape at all, irregular, chaotic. Galaxy shapes vary: thin disks, elliptical spheres, irregular, messy forms, disks, balls, chaos, the variety of galactic forms, from thin rotating disks to elliptical balls to structures without clear form. Galaxies take many shapes. Each shape tells a story of formation, of collisions perhaps, of quiet growth. But you don't need to read those stories now. Let galaxies be varied. Let them take whatever form they've taken. Magnetic fields thread through space, through galaxies, through galaxy clusters. Cosmic magnetic fields, they pervade galaxies and galaxy clusters, influencing the motion of charged particles. These fields are weak but vast, stretching across galaxies, affecting how charged particles move. Cosmic magnetic fields run through galaxies and clusters, guiding charged particles, magnetic fields, throughout cosmic structure, shaping particle motion. Galaxies and clusters are laced with these fields. Invisible, influential, fields you cannot see, but they're there. Guiding, directing. Let the fields weave silently through space. Future radio telescopes aim to understand these magnetic fields better, how they formed, how they evolved. A goal for future radio telescopes, tracing the origin and evolution of cosmic magnetic fields. Where did these fields come from? How did they grow? Future radio telescopes hope to answer this. Future radio telescopes, studying the formation and development of cosmic magnetic fields, origins, evolution, the history of magnetism in space. Future telescopes will explore this, tracing cosmic magnetic fields, their beginnings, their changes, a goal for future observations. You don't need to wait for the answer. The question can rest. Many galactic cores harbor magnetic fields near their supermassive black holes. These fields can shape jets. Magnetic fields near supermassive black holes in galaxy centers. They can form jets. In the cores of many galaxies, close to the central black hole, magnetic fields exist. These fields help shape jets of material, many galaxy cores, magnetic fields near the black holes. These fields can shape jets, jets of material streaming out, guided by magnetic fields near the central black hole. Magnetic fields in galaxy centers, near supermassive black holes, shaping jets, jets streaming out, shaped by invisible fields, near the galaxy's heart. Let the jets stream. Let the fields shape them, silently. Deep space is full of radiation, cosmic rays, high-energy particles. Cosmic radiation in deep space made of high-energy particles from supernovae and other extreme objects. These particles come from violent events, supernovae, other extreme cosmic sources. They travel through space at high energies, cosmic radiation, high-energy particles originating from supernovae and extreme objects, filling deep space, particles accelerated to tremendous speeds by explosions, by extreme magnetic fields streaming through the cosmos, deep space cosmic radiation, high-energy particles from supernovae and similar sources, radiation everywhere, particles moving fast, born in violence, traveling in silence. Let them travel. They've been moving for eons. In deep space, heavy ions are rare, but they contribute significantly to radiation exposure. Heavy ions, rare in deep space, but they carry significant radiation dose. Most cosmic radiation is lighter particles, but the heavy ions, though infrequent, are important. They deliver considerable radiation. In deep space, heavy ions are uncommon, yet they contribute significantly to the radiation burden. Rare, but significant. Heavy ions in the radiation environment of deep space. Heavy ions, infrequent. But when they hit, they matter. Significant radiation contributors. You don't need to fear them. Just know they're part of the environment out there. When radiation passes through spacecraft hulls, secondary particles can form. Secondary particles, created when radiation passes through spacecraft walls. These can affect sensitive tissues like eyes and skin. The hull blocks some radiation, but in doing so, creates new particles, secondary particles. These can reach astronauts inside. Secondary particles form when radiation goes through spacecraft walls. They can strike sensitive tissues, eyes, skin, radiation hitting the hull, creating secondary particles inside, reaching eyes and skin. Spacecraft hulls don't fully protect. They create secondary radiation, which can affect sensitive tissues. Protection is complicated. Shielding creates its own problems. Let the complexity rest. Engineers work on it. Inside a spacecraft, a kind of radiation bath forms. Residual radiation, fast neutrons, reaching even internal organs. A radiation bath forms in spacecraft from residual rays and fast neutrons, affecting internal organs too, not just the skin, not just the surface. The radiation environment inside a ship reaches deeper, internal organs. In a spacecraft, radiation forms a kind of bath. Residual radiation, fast neutrons, reaching internal organs, a bath of radiation inside the ship, permeating, affecting internal tissues. Inside the hull, a radiation environment persists. Fast neutrons, residual rays, reaching throughout the body. The body immersed in low-level radiation, even inside the ship. Let it be a technical problem. Let others solve it while you rest. This radiation environment is one of the most important medical risk factors for long crewed missions into deep space. The radiation environment, one of the primary medical risks for long crewed missions in deep space, for astronauts traveling far, for long durations. Radiation is a major medical concern. This radiation exposure, one of the most significant medical risks for deep space crewed missions of long duration. Long missions, deep space, radiation becomes a primary health risk. One of the most important medical risk factors, the radiation environment, for extended crewed journeys. A challenge for human spaceflight, radiation, health, long missions. Let the challenge exist. Let it be studied. You need not solve it tonight. Shielding in space is a compromise between weight, radiation protection, and other technical needs. Shielding spacecraft, a balance, weight versus protection versus other requirements. More shielding means more weight means more fuel, more cost, but less shielding means more radiation. Shielding is a compromise between mass, protection, and engineering constraints. A trade-off. Heavier shielding protects better, but adds mass, requires more propulsion, space shielding. A compromise between weight, radiation protection, and technical demands. Balance, always balance, between protection and practicality. Let the engineers balance, let the equations rest. Future habitats for long missions must integrate many things: radiation protection, living space, research areas, propulsion, all in one system. Future habitats for long-duration missions, combining radiation shielding, living quarters, research space, and propulsion. A habitat that protects, provides room to live, space to work, and moves itself. All together, long mission habitats must unify radiation protection, living areas, research facilities, and propulsion systems, everything integrated. Protection, life support, science, propulsion, future long-duration habitats, combining many functions, shielding, living, research, propulsion, complex systems, many needs, one vehicle. You don't need to design it, just know it's being imagined. Some concepts for deep space vehicles use large tanks as central living modules for crews. Deep space exploration vehicle concepts, using large tanks as habitats for crews. Fuel tanks, empty after use, repurposed as living space, pressurized, inhabited. Concepts for deep space vehicles, sometimes using big tanks as the main crew modules. Large tanks, originally for fuel, converted into habitats, living quarters for deep space. Deep space vehicle designs, large tanks serving as central modules for crews. Tanks as homes, in the depths of space. Let the concept float. Simple, efficient, strange. One habitat concept involves repurposing large rocket tanks as pressurized living spaces. In interplanetary space, a common habitat concept, reusing large rocket tanks as pressurized living spaces. For interplanetary travel, after a rocket tank empties, it could become a home. pressurized, sealed. A habitat in deep space, repurposing rocket tanks as living spaces. Pressurized in interplanetary space. A shared habitat concept. Large tanks, once full of fuel, now full of air and people. A habitat concept. Rocket tanks converted, pressurized, lived in, between planets, reuse, practicality, tanks becoming homes. These vehicles could serve as flying laboratories for experiments in microgravity throughout the inner solar system, deep space vehicles as laboratories, flying labs for microgravity experiments across the inner solar system, not just transport, but science platforms, places to conduct experiments in weightlessness while traveling. Such vehicles could function as flying laboratories, microgravity research. Throughout the inner solar system, laboratories that move, that drift between worlds, conducting experiments as they go. Flying labs, deep space vehicles for microgravity experiments, inner solar system, science in motion, experiments in transit. Let the laboratory drift, let the experiments float. Studies of trajectories show something interesting. A single deep space vehicle could support missions to both Mars and asteroids. Trajectory studies. One deep space vehicle supporting both Mars and asteroid missions. The same vehicle, different destinations. Mars, one time. An asteroid, another. One craft, multiple uses. Trajectory studies show a single deep space vehicle could support Mars missions and asteroid missions both. One vehicle, flexible paths. Mars, asteroids, both achievable. A single deep spacecraft, capable of Mars missions, capable of asteroid missions. Trajectory studies demonstrate this. Versatility. One vehicle, many destinations. You don't need to plan the mission, just know it's possible. For a crewed Mars mission, many fuel deliveries would be needed, dozens of them sent to Earth orbit to fully fuel the exploration vehicle. A crewed Mars mission requiring dozens of fuel deliveries to Earth orbit to fully tank the exploration vehicle. Not one launch, many, dozens of fuel shipments, each one adding to the total until the vehicle is ready. For a crewed Mars mission, dozens of fuel deliveries needed into Earth orbit to completely fuel the exploration craft. Dozens of launches, each carrying fuel, building up supply in orbit. For one Mars mission, dozens of fuel deliveries to Earth orbit. For fully fueling a crewed Mars exploration vehicle, many trips, much fuel. One mission. Let the fuel accumulate slowly. There's time. Future missions might test artificial gravity by rotating a habitat on a long arm. Future missions. Testing artificial gravity. A habitat rotating. On a long boom, spin the habitat. Create centrifugal force. Simulate gravity. On a long arm, extending from the spacecraft. Artificial gravity tests. Future missions. Rotating habitats on long arms. A habitat at the end of a tether. Spinning. Creating the sensation of weight. Future missions could test artificial gravity. Habitat rotation. On a long extending arm. Rotation. Centrifugal effect. Artificial weight. Let it spin in the future, slowly, steadily. One goal for these vehicles is modularity, so parts can be reused later on the Moon or Mars surface. A goal? Modularity, parts reusable on lunar or Martian surfaces later. Build it in pieces, use it in space, then land some pieces. Reuse them on a planetary surface. These vehicles aim to be modular, components reusable later, on Moon or Mars surfaces, modular design, so pieces can find new life on other worlds. Modularity as a goal, reusing parts on Moon surfaces. Mars surfaces, designed for reuse. From space to surface, nothing wasted, everything with a second purpose. Deep space exploration vehicles must function autonomously. For many months or years, deep space vehicles, autonomous operation. For months or years, no constant contact with Earth, no immediate help. They must work independently for long periods. Deep space exploration craft must operate autonomously, many months, perhaps years, months or years, on their own, functioning without constant oversight. Autonomous function required for deep space vehicles, months to years of independence, self-sufficient. For long durations, let them operate alone, in the silence, capable. Autonomous navigation systems can work with pulsars, natural cosmic lighthouses. Autonomous navigation using pulsars. Natural cosmic beacons. Pulsars spin, emit regular pulses, like lighthouses, and spacecraft can use these signals to navigate. Navigation systems using pulsars, which serve as natural cosmic lighthouses. Pulsars, regular, reliable, acting as navigation beacons across space. Autonomous navigation with pulsars. Natural cosmic lighthouses guiding spacecraft. Lighthouses in the cosmos. Pulsars, spinning, pulsing, guiding. Let them pulse, let them guide, steadily. X-ray pulsar navigation enables position determination in deep space. With accuracy around 1,000 kilometers, X-ray pulsar navigation, position finding in deep space. Accuracy of about 1,000 kilometers. By detecting X-rays from pulsars, spacecraft can determine their position, accurate to roughly 1,000 kilometers. X-ray pulsar navigation, positioning in deep space, accuracies around 1,000 kilometers. 1,000 kilometers sounds imprecise, but in deep space it's quite good. 1,000 kilometers accuracy. Position determination via X-ray pulsars. Deep space, around 1,000 kilometer accuracy. 1,000 kilometers. A small uncertainty across vast distances. Let the position be approximate. 1,000 kilometers is close enough out there. Algorithms for pulsar navigation combine measurements, time and direction of X-ray photons with data from gyroscopes. Pulsar navigation algorithms combining X-ray photon timing and direction with gyroscope data. Detect the X-rays, measure when they arrive, where they come from. Combine with gyroscope readings. Algorithms combine time and direction measurements of X-ray photons with gyroscope data for pulsar navigation, photon timing, direction, gyroscope orientation, all combined. Pulsar navigation algorithms linking X-ray photon measurements with gyroscope information. Data streams merging, time, direction, orientation. Let the algorithms process quietly, constantly. Evaluating these weak signals requires probabilistic filters, coupling position and attitude determination. Analyzing weak signals, probabilistic filters needed. Coupling position and attitude together, the signals are faint, the analysis complex. Probabilistic methods, linking where you are with how you're oriented. Evaluation of these weak signals requires probabilistic filters, combining position finding with attitude determination. Weak pulsar signals, analyzed with probabilistic filters, position and attitude linked. Probabilistic filters for weak signals, coupling position and orientation calculations. Faint signals, complex math, position and attitude intertwined. You don't need to understand the filters, just know they work, quietly, probabilistically. Such systems could supplement traditional radio navigation, work independently of the deep space network. these systems, supplementing traditional radio navigation, independent of the deep space network, not replacing Earth-based navigation, but adding to it, an independent backup. Pulsar navigation could supplement classic radio methods, operate independently from the deep space network. Supplemental navigation, independent, not reliant on Earth's network. Such systems could complement radio navigation, function independently of the deep space network. Another tool, another method, independence from Earth. Let the systems multiply. Let redundancy build. The Deep Space Network is a global network of large antennas, tracking spacecraft far beyond Earth orbit. The Deep Space Network, global antenna network, tracking spacecraft beyond Earth orbit, large dishes around the planet, listening, communicating with distant probes. The Deep Space Network, large antennas globally distributed, following spacecraft far from Earth. A network of antennas, worldwide, for deep space communication. The Deep Space Network, global, large antennas, tracking distant spacecraft, antennas, listening, around the world. Let them listen, day and night, to the far travelers. As more small deep space satellites launch, the network must handle communication time more efficiently. Growing numbers of small deep space satellites. The network must manage communication time better. More spacecraft, limited antenna time. Efficiency becomes essential. With increasing small deep space satellites, the network must use communication time more efficiently. More missions, same network capacity, efficiency required. Small satellites multiplying. Deep space network needing greater efficiency, more users, same resources, adaptation necessary. Let the network adapt. Let it learn efficiency. New operating modes emphasize on-demand access, supporting many spacecraft flexibly. New modes, on-demand access, flexible support for many spacecraft, not scheduled rigidly, but responsive, on-demand, flexible. New operational modes, on-demand access, to flexibly support many spacecraft, on demand, as needed, flexible scheduling, operating modes shifting to on-demand, for flexible multi-spacecraft support, flexibility, responsiveness, on demand. Let the scheduling shift, let flexibility grow. Shorter setup and shutdown times for communication windows can increase usable data transfer time. Shorter setup and shutdown for communication windows. More usable time for data transfer. Less time preparing. Less time closing. More time actually transmitting data. Reducing setup and shutdown times for communication windows. Increasing usable data transfer duration. Quick start, quick stop. More time in between for data. Shorter window setup and shutdown times. More usable time for transfer. Efficiency in the margins. More time for the actual work. Let the windows open and close quickly, maximizing the middle. Navigation data like Doppler and range measurements should also use less network time. Navigation data, Doppler, range measurements should require less network time. Even the navigation tracking, Doppler shifts, distance measurements should be more efficient. Navigation data, Doppler and range measurements should be gathered with less network time, less time for tracking, more time freed for other uses. Doppler and range measurements obtained with reduced network time. Efficiency in everything, even navigation. Let the measurements be swift. A goal is supporting a large fleet of small spacecraft simultaneously deep in the solar system. The goal, a large fleet, small spacecraft, all operating simultaneously, deep in the solar system. Many small probes, all active, all communicating, deep in space, all at once, a goal. Supporting many small spacecraft at the same time. Deep in the solar system, a fleet, distributed, operating together. Deep space, the goal. Large fleet of small spacecraft, simultaneous support. Deep solar system, many missions, one network, all operating. Let the fleet grow, let the network support them all. Today's deep space network is the communication lifeline for many missions to Mars, the outer planets, beyond. The deep space network today. Communication lifeline, Mars missions, outer planets, beyond, Mars rovers, outer planet probes, all depend on these antennas. Their lifeline, the current deep space network. Lifeline for many missions, Mars, outer planets, and farther. Lifeline, connection to distant missions. Today's deep space network, supporting missions to Mars, outer planets, beyond. The link, the voice, the lifeline. Let the signals travel. Let the lifeline hold. Small satellites in deep space need especially efficient radio systems because their antennas and power sources are limited. Small deep space satellites need efficient radio systems, limited antennas, limited power. Small means limited. Small antennas, small solar panels, small batteries. Efficiency matters. Deep space, small satellites require efficient radio systems because antennas and energy sources are constrained resources. Small platforms, efficiency essential. Small satellites, deep space, needing particularly efficient radio technology. Limited antennas and power. Small, limited, efficiency paramount. Let them be efficient. Small, but capable. New concepts combine communication links with scientific measurements. For studying the sun's environment, for example. New concepts, communication and science combined. Studying the sun's environment. The communication system also gathers data, dual purpose, talking and measuring. New concepts combine communication links with scientific measurements, such as solar environment research, communication as science, science as communication, combined. Combining communication with measurements for solar environment studies, for instance. Two purposes, one system. Let the systems serve double duty. Elegantly, autonomous control for spacecraft can be developed using reinforcement learning methods. Autonomous spacecraft control, developed with reinforcement learning. Teaching spacecraft to control themselves through reinforcement learning. Trial, error, learning. Autonomous control for spacecraft, developed via reinforcement learning methods, learning algorithms. Teaching spacecraft autonomy, reinforcement learning. For developing autonomous spacecraft control, learning, adapting, autonomous control. Let the machines learn, slowly, through repetition. For certain inspection tasks in orbit, a few discrete control commands may be sufficient for optimal performance. Orbital inspection tasks, sometimes a few discrete commands. Enough for optimal performance, not continuous control, just discrete choices, a few commands. And the task is done optimally. For some orbital inspection tasks, few discrete control commands can achieve optimal performance. Discrete choices, limited commands, optimal results, certain inspection tasks. Orbit, few discrete commands sufficient. Simple commands, effective results. Let simplicity suffice, where it can. For docking maneuvers, however, continuous control may give better results. Docking maneuvers, continuous control, better results. Docking is delicate. Continuous adjustment, smoother. more precise for docking maneuvers. Continuous control can deliver better results. Continuous, not discrete. Smooth adjustments for docking. Continuous control preferred. Smooth, continuous, precise. Let the control be continuous. Let the docking be gentle. A common goal. For many control strategies is fuel conservation while executing precise maneuvers. Control strategies. Common goal. Save fuel. Execute precisely. Precision with economy. Accurate maneuvers without wasting fuel. Many control strategies share a goal. Conserve fuel. Still achieve precise maneuvers. Fuel conservation. Precision. Both. Common goal. Save fuel. Maintain precision. Efficiency and accuracy. Together. Let fuel be conserved. Let precision remain. Future spacecraft might make more decisions on board rather than waiting for instructions from Earth. Future spacecraft, more onboard decisions and less waiting for Earth. Autonomy increasing, decisions made aboard. No need to wait for the signal from home. Future spacecraft could make increasing decisions on board instead of awaiting Earth instructions. Onboard autonomy, independent decisions, more decisions made aboard future spacecraft. Rather than waiting for Earth, independence growing. Decisions local. Let them decide. Out there, on their own. Long communication delays in deep space make this autonomy especially important. Deep space. Long communication delays. Autonomy essential. Light takes time, minutes, hours. Waiting for instructions is impractical. Long communication times in deep space make autonomy particularly important. Delays make autonomy necessary. The farther you go, the more you must decide alone. Communication delays. Deep space, making autonomy especially important. Distance, delay, autonomy. Let autonomy be necessary. Let it be embraced. Atom interferometry experiments with ultra-cold gases have been moved to space. Atom interferometry, ultra-cold gases. Experiments now in space. Physics experiments. Atoms cooled almost to absolute zero, now conducted aboard spacecraft. Atom interferometry experiments. Using ultra-cold gases, moved into space, space-based. Ultra-cold atoms, interferometry. Experiments with ultra-cold gases. Atom interferometry, relocated to space. Cold atoms. Quantum experiments, in orbit. Let the atoms be cold. Let the experiments float. In weightlessness, these experiments achieve especially long interaction times with gravity. Weightlessness, long interaction times with gravity. On Earth, atoms fall quickly. In space, they float longer. Interact with gravity's subtle effects longer. In weightlessness, these experiments, particularly long interaction times with gravity, longer observation, longer measurement. Weightlessness allows it. Weightlessness enables especially long gravitational interaction times. For these experiments, long times, subtle effects measured. Let the atoms float, let gravity act. Slowly. Ultra-cold atoms enhance quantum effects. Make tiny differences in gravitational fields measurable. Ultra-cold atoms, enhancing quantum effects. Making small gravitational differences measurable. Cold amplifies quantum behavior. Tiny gravitational variations become detectable. Ultra-cold atoms amplify quantum effects. Make tiny gravitational field differences measurable. Quantum enhancement. Through cold. Measuring minute gravitational variations. Ultra-cold atoms. Quantum effects enhanced. Tiny gravitational differences measured. Cold. Quantum. Sensitivity. Let the atoms be sensitive. Let them measure the subtle. Dual-species atom interferometers compare freely falling atoms of different types. Testing equivalence principles. dual species interferometers, comparing freely falling atoms of different kinds, testing equivalence principles, two different atoms, both falling the same way, equivalence tested. Dual species atom interferometers, comparing free-falling atoms of different types, testing equivalence principles, different atoms, same gravity, the question tested, comparing different atoms, free fall, testing equivalence. Dual species interferometry, two species, one fall, equivalence questioned. Let the atoms fall together. Let the comparison be made. In space, these instruments reach temperatures near absolute zero. In space, these instruments, near absolute zero temperatures, almost as cold as possible, nearly the coldest temperature achievable. These instruments achieve near absolute zero temperatures. In space, cold, almost absolute zero, near absolute zero. The temperatures these instruments reach, in space, cold, nearly the coldest. Let the cold be extreme. Let the measurements be precise. Such missions try to bring gravity and quantum physics together in one experiment. These missions, uniting gravity and quantum physics in single experiments, two fundamental forces, two theories, brought together experimentally. Such missions attempt to combine gravitation and quantum physics in one experiment. Gravity, quantum mechanics, together, experimentally. Missions bringing together gravity and quantum physics. One experiment, two realms, one test. Let the theories meet. Let the experiment proceed. Quantum sensors in space could enable future navigation systems and tests of fundamental constants. Quantum sensors in space for future navigation, testing fundamental constants, sensors using quantum effects, potentially navigating spacecraft, measuring whether constants truly stay constant. Space-based quantum sensors could enable future navigation systems and tests of fundamental constants. Navigation, fundamental physics, both possible with quantum sensors in space. Quantum sensors in space, future navigation, testing constants, precision tools, multiple purposes, quantum-based. Let the sensors sense. Let constants be tested. The icy moons in the outer solar system are considered especially interesting targets for astrobiology. Icy moons, outer solar system, particularly interesting for astrobiology. Moons covered in ice, orbiting distant planets, potential homes for life, astrobiologically compelling. The icy moons of the outer solar system, especially interesting targets for astrobiology. Outer solar system, ice-covered moons, astrobiology's interest. Icy moons, outer solar system, considered particularly interesting. Astrobiology, ice, distance, possibility. Let the moons orbit. Let the interest remain. Europa's surface is made of ice. Beneath it, very likely, hides a deep, salty ocean. Europa, ice surface. Beneath it, high probability, a deep salty ocean, ice on top, water below, salt dissolved in it, an ocean under the ice, Europa's surface, ice underneath with high probability, a deep salty ocean, Europa, frozen surface, hidden ocean below, salty, deep, Europa, ice surface, likely concealing a deep salty ocean beneath, ice above, ocean below, salt within. Let the ocean hide beneath the ice quietly. Magnetic field measurements first indicated this subsurface ocean. Magnetic field measurements, first hints of the subsurface ocean. Europa's magnetic behavior, strange, suggesting liquid water beneath, conducting, moving. Magnetic field measurements initially pointed to this underground ocean, magnetic readings. First indication, ocean below, magnetic field measurements. First suggesting the subsurface ocean's existence. Magnetism, evidence, ocean implied. Let the magnetic fields tell their story. In Europa's ice shell, processes like convection and diaparism might mix ice and ocean. Europa's ice shell, processes like convection and diaparism, could mix ice with ocean, ice moving, warmer ice rising, colder sinking, diapirs forming, ice and water mixing. In Europa's ice shell, convection and diaparism might provide mixing between ice and ocean, mixing processes, convection, diaparism, ice shell and ocean interacting. Convection and diaparism in Europa's ice shell could mix ice and ocean, movement within ice, mixing with ocean below. Let the ice flow, let mixing occur. Slowly. The Europa Clipper mission will determine the ocean's depth, salinity, and thickness more precisely. Europa Clipper will determine ocean depth, salinity, thickness more precisely. A spacecraft orbiting Jupiter, flying by Europa repeatedly, measuring, refining our knowledge, the Europa Clipper mission will more precisely determine this ocean's depth, salinity, and thickness. Clipper, measuring, depth, salt, thickness. Europa Clipper, determining ocean depth, salinity, thickness. More accurately, measurement mission, precision, understanding. Let the mission measure. Let the ocean be characterized. The mission will also investigate possible water plumes, erupting from cracks in the ice into space. The mission, investigating possible water plumes from ice cracks spraying into space, geysers, perhaps, water erupting through cracks into the vacuum, plumes of ocean material. The mission investigates possible water plumes that spray from ice cracks into space, plumes, water, from cracks into space, investigating possible water plumes erupting from cracks into space. Europa Clipper's task, water escaping through ice into vacuum. Let the plumes spray, if they exist. Let them be found. Such plumes could release ocean material without needing to drill through the surface. Plumes, releasing ocean material. No drilling needed. If plumes exist, they carry ocean contents upward, accessible. No need to dig. Such plumes could release material from the ocean without drilling through the surface. Ocean samples, delivered to space by plumes. No drilling required. Plumes, if present, could release ocean material without surface drilling. Access without penetration. Plumes as windows. Let the ocean present itself through plumes, naturally. The combination of energy sources and liquid water makes Europa a possible location for simple life. Energy sources and liquid water combined make Europa a possible place for simple life. Life needs energy. Life needs liquid water. Europa might have both. The combination of energy sources and liquid water makes Europa a possible location for simple life. Energy, water, life's requirements, possibly met on Europa. Energy sources, liquid water, together on Europa, making it a possible life location. Possibility, not certainty, but possibility. Let the possibility remain. Let it be investigated. Ocean worlds in the outer solar system show that habitable environments can hide deep beneath ice. Ocean worlds, outer solar system, examples, habitable environments hidden under ice, life-friendly conditions, not on the surface, but deep below, under kilometers of ice. Outer solar system ocean worlds, examples that habitable environments can exist deep beneath ice, habitable zones, underground, ice-covered, hidden. Ocean worlds in outer solar system, show habitable environments can be deeply ice-buried. Habitability, hidden, under ice. Let habitability hide. Let ice conceal possibility. Many exoplanets we know are larger than Earth, so-called super-Earths or mini-Neptunes. Many known exoplanets, larger than Earth, super-Earths, mini-Neptunes. Planets around other stars, often bigger than our world, in between Earth and Neptune in size. Many exoplanets we know, larger than Earth, called super-Earths or mini-Neptunes. Super-Earths, mini-Neptunes, larger than Earth, common among exoplanets, many known exoplanets, larger than Earth. Super-Earths, mini-Neptunes, bigger worlds, around distant stars, common. Let them orbit, let them be larger. With infrared data, atmospheres of some exoplanets can be studied for clouds or specific molecules. Infrared data, studying exoplanet atmospheres, looking for clouds, specific molecules, light passing through atmosphere, infrared wavelengths revealing composition, clouds, gases, using infrared data. Exoplanet atmospheres can be examined for clouds or certain molecules, atmospheric studies, infrared, clouds, molecules, infrared data, examining exoplanet atmospheres, clouds, specific molecules, infrared, atmosphere, composition. Let the atmospheres reveal themselves. In infrared, gravitational lensing can also help detect isolated exoplanets or free-floating planets without stars. Gravitational lensing, detecting isolated exoplanets, free-floating planets, starless, planets without suns, drifting alone. Lensing can find them, gravity revealing their presence. Gravitational lensing can help find isolated exoplanets or free planets without stars. Lensing, finding planets, even those without stars. Gravitational lensing, detecting isolated exoplanets, free-floating planets, planets alone, starless, detectable through lensing. Let the lonely planets be found through bent light. Deep JWST catalogs contain objects across a wide redshift range, from nearby galaxies to very early systems. Deep JWST catalogs, wide redshift range, nearby galaxies, very early systems, objects at many distances, many ages, all catalogued, from close to incredibly far. Deep JWST catalogs, objects across wide redshift range, nearby galaxies to very early systems, wide range, near and far, JWST catalogs, deep, objects spanning wide redshift, nearby to very early, distance, time, all represented. Let the catalog span, near to far, young to old. From this data, researchers reconstruct star formation histories across all cosmic time. From this data, star formation histories reconstructed across cosmic time. When did stars form? How fast? Over billions of years. The data reveals this. From these data, researchers reconstruct star formation histories over all cosmic time. Star formation mapped across time, reconstructing star formation histories from JWST data across cosmic time, history written in starlight across ages. Let the history be reconstructed. Let the stars tell their timeline. The discovery of many very early massive galaxies challenges some galaxy formation models. Many early massive galaxies discovered, challenging some formation models. Galaxies that shouldn't be so massive so early, yet they are. Models questioned. Discovering many very early massive galaxies challenges some galaxy formation models. Early, massive, unexpected. Models challenged near. Many very early massive galaxies discovered. Challenging formation models. Surprise, early mass, theory adjusting. Let the models adapt. Let the data lead. Even before Webb launched, astronomers planned its role as Hubble's successor. Before Webb's launch, astronomers planning its role as Hubble's successor. Hubble's air, designed before launch, intended to continue, to go further. Before the Webb telescope launched, astronomers planned its role as Hubble's successor. Pre-launch planning. Webb as successor to Hubble. Even before launch, Webb's role planned, Hubble's successor. Succession, planned, continuity. Let one telescope follow another. Let the vision continue. Webb sees primarily in infrared light, especially important for early distant galaxies. Webb, primarily infrared, important for early distant galaxies. Infrared reveals redshifted light, light stretched by cosmic expansion. From the earliest galaxies, Webb sees mainly in infrared light, particularly important for early distant galaxies. Infrared vision, early galaxies, especially relevant. Webb, infrared primarily, especially important for early distant galaxies. Infrared, early light, distant sources. Let infrared reveal what visible light cannot. Webb's first published deep field image showed thousands of galaxies and many gravitationally distorted light arcs. Webb's first deep field, thousands of galaxies, many gravitationally distorted arcs. One image, thousands of galaxies. Light bent into arcs, lensed. The first published Webb deep field image showed thousands of galaxies, many gravitationally distorted light arcs. First deep field, thousands of galaxies, distorted arcs. Webb's first deep field, thousands of galaxies, many gravitational arcs, thousands, arcs, one image. Let the first image contain multitudes. Some of these arcs come from galaxies whose light was traveling to us long before our solar system formed. Some arcs from galaxies, light traveling to us before our solar system formed, ancient light, older than the sun, older than Earth, finally arriving. Some of these arcs from galaxies whose light traveled to us long before our solar system existed, light older than the sun, than Earth. Some arcs from galaxies, light en route before our solar system's formation, ancient photons predating home. Let the ancient light arrive, finally. After all that time, deep fields let us see different cosmic epochs simultaneously, because light from different distances has traveled different durations. Deep fields, different cosmic epochs, seen simultaneously, different light travel times, near and far in one image. Recent and ancient, different travel times, one view. Deep fields show various cosmic epochs at once, because light from different distances travel different durations. Simultaneity of ages, different travel times, one image, deep fields, simultaneous cosmic epochs, different light travel durations, all history. One glance. Let all ages be present in one image together. Each small point of light in such images is usually an entire galaxy with billions of stars. Each small light point, usually an entire galaxy, billions of stars. A dot, but not a star, a galaxy. Billions of stars within that dot. Each small point of light in such images, usually an entire galaxy, with billions of stars, points, galaxies, billions of stars each. Each small light point, an entire galaxy. Billions of stars, dots, galaxies, multitudes. Let each point contain billions. Let the scale be incomprehensible. With each new observatory, the boundary of the deepest view into the cosmos shifts farther out. Each new observatory, deepest view boundary, shifting farther, we see farther. With each advance, each new telescope, deeper into space, further into time. With each new observatory, the limit of the deepest cosmic view shifts farther outward. Progress, deeper views. Each generation, each new observatory, pushing the deepest view. farther out, farther, deeper. With each tool, let the boundary recede, let the view deepen. Our view of deep space is always a journey into the past, never a look at the current state of distant galaxies. Deep space viewing, always into the past, never the current state of distant galaxies. We see what was, not what is. Light takes time. We see the past. Our view of deep space, always a journey into the past, never the current state of distant galaxies. Past, not present. Always. Deep space views, into the past, never current states. History, not now, always then. Let the past be what we see. Let now remain invisible at distance. Even as we look farther out, most of the universe remains fundamentally invisible, due to dark matter and dark energy. Looking farther, yet most remains invisible. Dark matter, dark energy, we see more, but most stays hidden. Dark matter doesn't shine. Dark energy leaves no direct trace, even looking farther. Most of the universe remains fundamentally invisible because of dark matter and dark energy. Invisible majority. Dark matter, dark energy. Most universe, invisible. Dark matter, dark energy. Even as we look farther, invisible, dominant, unknown. Let the invisible remain. Let the mystery persist. Nevertheless, these faint signals and distant galaxies tell us, step by step, the story of the universe's origin and evolution. Nevertheless, faint signals, distant galaxies, telling us, step by step, the universe's story. Bit by bit, signal by signal, galaxy by galaxy, the story emerges. Origin, evolution. Nevertheless, these faint signals and distant galaxies tell us step by step the story of the universe's origin and evolution. Story unfolding gradually through faint signals, distant galaxies, telling the story step by step. Origin, evolution. Story told slowly by distant light. Let the story be told. Let it unfold step by step. Let the signals arrive. Let them speak. Let the universe reveal itself slowly across time. There's no need to understand it all, no need to remember. The universe has been here. It will continue. You can rest now. Let the cosmos drift. Let the stars form. Let the galaxies turn. Let the light travel. All of it continuing without effort. You need do nothing. The universe proceeds. Rest. Let go. Drift. The cosmos is patient. You can be patient too. Nothing here requires you. Nothing asks for your attention. Let it all be. Let yourself rest. The deep space, the distant galaxies, the ancient light, all of it continuing in silence. And you, here, now,
can simply rest. Let the darkness be gentle. Let sleep come. The universe will still be here, expanding, evolving, slowly. You can let it go. Let yourself drift into rest. Nothing to hold, nothing to remember. Just rest, just peace, just sleep.